So I want to work through the 3-question review for this unit, starting with I have f of x being minus log base 3 of x plus 5. I want to sketch the graph of the inverse of it. So a few options. One is to sketch the graph of f of x and then visualize the inverse, or what I think is a bit less work is to just find the inverse equation. And so let me start this in a very standard way in which I'll write f of x as y equals minus log base 3 of x plus 5. If I want to find the inverse, I want to swap my inputs and outputs, or my x and y. So I have x equals minus log base 3 of y. Almost wrote an x there. Y plus 5, and then solve for y. First thing I would do is multiply both sides by -1, or divide both sides by -1, so I don't have that -1 coefficient in front of the log base 3. So I have negative x equals log base 3 of y plus 5. I then write this in exponential form. So I have 3 to the power of negative x equals y plus 5. Now I'm virtually done. Subtract 5 from both sides. So I have y equals 3 to the negative x, take away 5, or really that is my inverse. Oops, I'm not very careful today. Inverse of f of x is 3 to the negative x minus 5. All right, so now I want to graph this. And so this is the graph of 3 to the power of x reflected horizontally and move 5 units down. So first 3 to the power of x, I'll just visualize it quickly. It goes through 0, 1, 1, 3, 2, 9. So here's 3 to the power of x. Now I want to imagine, I want to reflect those points over the y-axis, or reflect it horizontally, which means it'll still go through here. It'll go through here now, end up here, and then just move this 5 down. So as soon as I move it 5 down, I can see there's going to be an asymptote at -5 on the where y equals -5 down there. And if I just move these points all 3 down, it should have a y-intercept of -4. It should go through -1, -2, and it should also go through a -2, 4. And I'll draw my curve. In general, whether we have 2 or 3 points, and the nice thing about having 3 points is if I just have just these 2 points, they're so close to each other, we may not feel very confident with how the rest of it looks. All right, so that's the graph of the inverse of f of x. So second part, determine a value of x such that f of x equals -3. So for this, I'm just going to write down the equation for f of x again, which is what was given, minus log base 3 of x plus 5, and I'll just make that equal -3. There's other approaches, but this is probably the quickest to solve. I would first multiply both sides by -1 to make this just log base 3 of x plus 5 equals +3. I'll write this in exponential form. So I have 3 to the power of 3 equals x plus 5, which means 27 equals x plus 5, which means x equals 22. And before I feel too confident, let's always make sure we just realize that we should just check. And I just got to go back to my original equation and just make sure that when I put a 22 in there, I don't have a negative in my logarithm, which I clearly don't. I don't need to do more than that. I'm done. All right, next, 3 different approaches on the same setup. I have some amount, maybe it's a population, maybe it's probably a population of bacteria or something, but it doesn't matter. It grows exponentially such that it doubles every 5 hours. All right, so first I want an equation that models this as a function of time in hours. So since I don't know the initial amount, I'll just call it A0, and the final amount will equal the initial amount times. I'm saying that it doubles, so one of the most common approaches is to just have this multiplied by 2, but not every hour, every 5 hours. So if I put a t up here, that would be correct if it doubled every hour. Every hour, the initial amount gets multiplied by 2. It's every 5 hours, so I want to slow this down. So it's not t, it's t over 5. And that's it. I've done that first part. If it doubled every 6 hours, it'd be t over 6. And again, if it doubled every hour, it'd just be to the power of t. All right, that said, for the second part, what if I want to have it with a base of 3? Because honestly, I could have any base there. Just a base of 2 just was the most pleasant for how the information was given to us. So how could I figure this a similar equation out in the same form but with a base of 3? Well, if I'm going to have a base of 3 here, that's really, I need to think about how often does it triple? What's the tripling time of this? And so I have an equation already. So let's find how long it takes for this population of whatever to triple. And so I'm going to take my equation from before. A equals A naught times 2 to the power of t over 5. But if I want to find how long it takes to triple, then I want this A naught to become 3 times bigger. So I can choose anything I want for my A naught. I'm going to be boring and simple and make it 1, which means if I want it to triple, I want to find how long it takes for this to get to 3. It doesn't really matter what I pick for my initial amount as long as my final amount is 3 times more, which means I don't really need that coefficient of 1 there. And now I can solve for t, and this will tell me how long it takes to triple. So if I want to solve for t, I would put this into logarithmic form. I'd say log base 2 of 3 equals t over 5, which means t equals 5 times the log base 2 of 3, which is approximately 7.92, which tells me it takes this population or this amount 7.92 hours to triple. And that's now what I need for this part right here. If I go back to my question, I now know that just shy of every 8 hours, this population triples. And so therefore, I can now answer the question. The amount after any time is the initial amount, which again, we don't know, times 3 to the power of t over 7.92. And since that really is rounded, I'm going to make this equal sign an approximate sign. Because keep in mind, once I found that value that I've highlighted in green that takes 7.92 hours to triple, then it's really no different than the first question, in which it doubles every 5 hours, it triples every 7.92 hours. Very similar setup. I like the first equation better, but anything is possible. Lastly, I can also express this equation in the form A naught times e to the RT. To do this, I need to figure out the rate of growth or decay. I know it's a growth because it's getting larger, so I need to calculate that. And so to figure this out, if I just start with this general form, how can I find that rate of growth? Well, let's think back to what we're told in the beginning of the question. It doubles every 5 hours, which means whatever my starting amount is, again, I'll be simple and make it 1. I know it's going to double, which means the final amount is going to become 2 in 5 hours. So that means my time here will become a 5. So I have r times 5. That's just going back to what was told in the first part of the question, which keep in mind, again, I don't need that coefficient of 1, so I'm going to get rid of it. I want to solve for this. Again, I want to put this in logarithmic form. So I want to write the log base e, or the natural logarithm of 2, equals 5r, which means r equals the natural logarithm of 2 divided by 5, which is approximately 0.139. And so with that said, now I know my r value, my rate of growth in this case, approximately. And so now I can use that to actually find my equation. So the equation, the final amount will be the same as the initial amount times e to approximately 0.139 times time in hours. And again, because that was approximate, I really should put a squiggly equal sign there. So of these 3 equations, this one here, and this one here, they're all equivalent. In many ways, you might like the first equation the best, although if you learn calculus and we have to find derivatives of things, for example, that this last equation is much more pleasant to work with. Either way, last question. I have a scatter plot, again, of some sort of information. What do I know when x is 0, the value of the function is at 6, and that's the only point I know for sure. So my starting amount is at 6. So I want to find an equation for this in any way. There's lots of ways we can do this. That said, I'm going to pay attention to the first point as well as the last point, because whatever error I may have in my approximations here, I can minimize it by looking at as the farthest point in the data as possible. So this point seems to be about, if I look at my scale, this is 700, so I can see my vertical axis is going up in 25s. Going up in 50s, and this is roughly halfway through. It's a little more, but it looks like this is at approximately 825. When the y, that's the y value, when x is 20. which means I know from here to here, it goes up by some amount. I'm going to calculate. We multiply by some amount in 20 units, 20 days, 20 hours, 20 years, whatever. So first, to go from 6 to roughly 825, that means I want to figure out what that is. I just want to go 825 divided by 6. And if I go 825 divided by 6, I get approximately 137.5. I say approximate because that's not actually necessarily 825. So I know that to go from x equals 0 to x equals 20, I multiply by about 137.5. So one way of thinking about this is whatever this function is, it grows by 137.5 times in 20 units on x, in 20 days, 20 hours. Which means this is actually quite similar to this question here. Here I said it doubles, which is a nicer number, every 5 hours. Here it doesn't double. It gets 137.5 times bigger. Not every 5 hours, every 20 units. And so I can then say, okay, my final amount, or even actually in this case, I say it's g of x. So I'll say g of x is the starting amount, which we do see is 6 times 137.5 to the power of x over 20, because it takes 20 units to get 137.5 times bigger. And again, if I want to be picky, I really should change these equal signs to an approximate sign. That said, I now want to use this to determine the value of g of 18. Now, let me clean up my graph a bit here. So g of 18, that means when x is 18, which I can see is right here. That said, what is the value? Well, let's just take my x equals 18 then and just substitute it into here. And I should get a value that seems to fit the curve that we can visualize on the grid here. And so I can say right here that g of 18 will equal 6 times 137.5 to the power of 18 over 20. Quick little bit of work under my calculator. If I use these values, I get around 500, which let's just make sure if that looks kind of right. That means when x is 18, y or g of x is about 500, which brings me to right along this point right here. And that looks pretty good, because if I imagine a exponential growth curve, that seems about right. So I can feel pretty confident about that value. Whereas if I made a mistake and got like 200, which would be like right here, I can be 100% confident there's something wrong there. All right, last part, use your equation from part A to determine the value of the inverse g at 1. And maybe before I go on, I should say, even if you came up with a slightly different, if you had a different equation here and you weren't sure if it was correct, well, for part B, you should get really close to 500. If you do, you know you're right. If you don't, you know you're wrong. And so that's where there's a lot of variety here. But for part C, where I want to use the inverse, again, if we know our equation is correct, which I now know it is, I'm going to use the equation I had from part C. So again, which was 6 times 137.5 to the power of x over 20. I'm going to use that equation for g of x. But I want to find the value of the inverse at 1, not g at 1. So I have a few options. One option, since I'm trying to find the value of the inverse at 1, is to actually find the inverse of this function. I'm not going to do that because I'd get a logarithm of base 137.5, which is nothing wrong with that. But I don't actually need to find the equation of the inverse to figure this out. All I need to do is figure out what's the value of the inverse at 1. And we want to remember again, inverses and functions are all, the inputs and outputs are swapped around. So trying to find the value of the inverse when we put 1 inside the inverse, that's the exact same idea as finding the value of this function when 1 comes out. Again, putting 1 into the inverse, same as 1 coming out of our function. So I can just take this equation and just make it equal 1 and figure out what number must go in. Because again, putting a number into an inverse is the same as the number that comes out of the original function. And in my opinion, this is significantly less work since I don't actually have to find the equation of the inverse. So now I want to solve this equation here. Divide both sides by 6. I get 1/6 equals 137.5 to the power of x over 20. I want to put in logarithmic form, so I get log base 137.5 of 1/6 equals x over 20. Multiply both sides by 20, and I can see x will equal 20 times the log base 137.5 of 1/6. Now it's just a matter of calculator work, and you should get approximately negative 7.3. And again, even if you use a different exponential model for the data, you should get an answer extremely close to this. I say extremely close because, again, this value of 825 up here that I use, it isn't actually exactly that, and so, but there's a very, very, very small range of answers that would be correct.